It's a pleasure to welcome all of you to the 2020 Schawlow-Townes Symposium. This is the ninth in our series, ninth symposium in our series, but of course COVID-19 forces a different format than any others. So we've chosen a 3-day format covering just a short amount of time each day. But we've tried to keep the essential pieces of the Schawlow-Townes Symposium intact. So we have a major speaker, one of the leaders of photonics in the world, always paired with a younger speaker, a rising star. And then we follow it by a poster session. And for each of you who wishes to attend a poster session, I recommend that you upgrade, if you haven't done so already, to Zoom 5.3. That allows you to enter the session and go from poster to poster to poster as you wish. So 5.3, Zoom 5.3, it only takes a minute to update it. And then once you're entering the poster session, each room will have a name on it, and you can enter any room as you wish, like an ordinary poster session. Now, I'm going to turn this over to Bob Boyd. Bob will now tell us about the history of the Schawlow-Townes Symposium and go on to introduce our first speaker. Bob.
So, hello everybody, and I welcome you to this, the 2020 edition of the Schawlow-Townes Symposium. As Paul Corcoran just reminded us, this is the 9th edition of the Schawlow-Townes Symposium. The history is that in 2010, I had just taken a position at the University of Ottawa. Paul and I met to talk about what I could do as a professor at the University of Ottawa to advance the field of photonics and to show the world that we were very serious about photonics in Ottawa. We chose the name Schawlow-Townes Symposium. I hope you're seeing this. We chose the name Schawlow-Townes Symposium in Photonics to honor two of the giants in the field of photonics, Arthur Schawlow and Charles Townes.
You would have to share your screen, sorry, at the bottom.
I'm not sharing my screen. Oh. Okay, do people see the screen now?
Thank you, yes.
Okay, so sorry for that confusion. So this is the 2020 version of the Schawlow-Townes Symposium. The symposium was, Paul Corcoran and I decided to name the symposium after two giants in the field of photonics, Arthur Schawlow and Charles Townes. In fact, this photograph of Charles Townes was at the very first Schawlow-Townes Symposium, where he came and gave one of the speeches to the audience. Turns out Art Schawlow was Canadian, and his sister was married to Charles Townes. So that made Professor Townes almost Canadian, or Canadian by marriage. So let me now introduce our first speaker. Our first speaker is Gerard Nuru. I have known Dr. Mourou for a very long time. He and I were both on the faculty at the University of Rochester in the 1980s. And I can still recall discussions that he and I had where he explained to me the concept of chirped pulse amplification. Now, of course, his idea worked exceedingly well and was the basis of the Nobel Prize in Physics that he received jointly with Donna Strickland in 2018. Little bit of biography of Gerard. He was born in Albertville, France. He studied physics at the University of Grenoble and at the Université Pierre-Marie Curie in Paris, where he earned the Ph.D. degree in 1973. He later moved to the United States, where he became a professor at the University of Rochester, which is where he did his Nobel Prize winning work with Donna Strickland. He subsequently worked at the University of Michigan and at École polytechnique in Paris. So I'm very pleased now to turn the screen over to Gerard. He always gives fascinating and inspiring talks about the potential, the things we can learn about the world around us using high intensity lasers. So Gerard, we're so pleased to have you with us here.
Okay, well, good morning, ladies and gentlemen. It's a pleasure to be with you from a long distance because I'm in Provence, in France. And fortunately, I couldn't be with you. I'm going to talk about some of the novel ideas we have to use ultra high intensity lasers, you know, for applications in science, but medical and also in environment. I just want to remind you that really with extreme light, we can produce now, you know, the largest peak power, the largest temperature, the largest pressure, the largest acceleration, the largest field. It is a universal source of high energy particle and radiations. And what is exciting now is that we can really go from the atomic physics where we were before, when we were using just normal laser, normal intensity, to subatomic physics. So we are going to move from electron volt physics to tera-electron volt physics. Here is my slides and my curve, I should say, where you can see, you know, the intensity as a function of times since, you know, the first laser from Mayman. And you just recognize that we have, you know, in the 60s, very, very fast rise. And then a plateau, which is due to the fact that we cannot really amplify pulses due to the nonlinear effect that we are producing. And then with Donna, we came up with the idea of CPA. Now with CPA, what's remarkable right now is you can go to very, very high intensities up to, I think, soon to be up to 23, 24. When we are in this regime, you know, of course, what we likely to go is to go above the 25 and to up to 29. Why do you want to do that? Because in this intensity level, you can really materialize light. And so the question is now, how can we go to 10 to the 29? How can we go to the Schwinger limit? Well, we have two options. The first option is, if you want really to increase the intensity, is really to to increase the energy, because of course power or intensity is energy divided by time. So you can increase the intensities, or the other options is to decrease the pulse durations. Increasing the intensity, increasing the energy is very difficult and very expensive. If I show you, for instance, this is what we try to do with the ELI infrastructures. And you see that we have these three beautiful facilities where we have really three humongous lasers. And of course, they are at the 10 petawatt level. If we want really to go much, much higher, we would have really to spend a lot of money, okay? And which is not very exciting. So what we prefer is maybe trying to use the second scenario, which is really trying to compress the pulse. Okay, right now pulses are in a 20 femtosecond or so, which means we have about 7-8 cycles, and we would like really to go to a single cycle. Single cycle, of course, indivisible right now. Okay, and then we will see how we can go even further. So right now, the first step is trying to take a 20 femtosecond pulse and trying to cram the cycles into a single one of about 2 femtoseconds. So in order to do that, we are going to use what we are using with capillaries, and which has been introduced, in '85 by the people like Schenck and so on, and where we are using fibers, okay, to produce, to increase the bandwidth of the lasers. What we, so this is what, make us possible to reach the 6 femtosecond pulses and uses, which equivalent to about a few cycles, okay. Now, the problem with that, if we are using just single fibers, we are limited to energy in a nanojoule regime. And so in order to go much higher, to go to the millijoule regime, then we have people like Horacio Svelto and so on, who had the idea to use capillaries. Capillaries, make possible to really now to send not nanojoules, but to go to the millijoule level. Okay, and also it was shown that by using we could produce millijoule also in in a single cycle, in few cycle regime. That has been demonstrated in a number of labs. Now, what we like to do is to go much higher. Okay, we like to go to the joule level, maybe to the kilojoule level. Okay, so of course we cannot really use now capillaries because we cannot really handle joules into capillaries. So the idea now is really to use thin plates or thin films, okay, to produce the cell phase modulation that we need. And what is nice with thin plates can accommodate top hat lasers, the type of top hat that we can produce now with lasers. Okay, if I'm using this top hat, then I can really produce cell phase modulations on the thin films over a large area. And so, we will have uniform cell phase modulation across the beam. And then, when we have that, we will compress the beam, like we do normally. So, so this is the type of material that we are using. There can be thin films or plates of silicate, for instance. Okay. So now we are going to do that, and the experiment is being done in a number of places. We are trying to coordinate, all these activities. But usually what we do is we start with a 25 femtosecond lasers. Then we have a thin films of hundreds of micrometers or so, or thin plates, for that matter. And then we are producing cell phase modulations, which means that we are broadening the spectrums. And we are using the group velocity dispersion in the film really to stretch the pulse. So in the first stage, we are producing this cell phase modulation and group velocity to produce this pulses, which is now in a regimes of femtoseconds, okay, few femtoseconds, and now we are going to use chirp mirrors, just chirp mirrors, in order to compress it to the 5 femtosecond regime. And now with a 5 femtosecond regime, the idea is now to go into a second stage where we are going to first to go through a thin films and do the same thing. We are going to now produce broadening, okay, due to the thin film. And then we are going to compress the pulse now, which has the spectrums for 2 femtosecond pulses. We are going to compress the pulse using a second compressor composed of mirrors with gradients. So we have 2 femtosecond pulses now. And of course, these experiments are being done in a number of places, okay? And you can see, for instance, on your left inside, the black curve is the initial pulse. The red curve is the first stage, the pulse after the first stage, and the blue curve is the pulse after the second compressor. Okay, these of course are simulations, but now we can really produce something close to that. We did first really very convincing experiment with the Pearl system in Nizhny Novgorod in Russia, and where we are compressing a pulse of a duration of 75 femtoseconds into 15 femtoseconds. Okay, and now we are trying to go to do the same thing from 20 femtoseconds to sub 10 femtoseconds, and this in order to demonstrate the first stage of the experiment. Now the question is, I think we are going to go close to single cycles, but we are in a visible regime, okay? So we would like to go much shorter, and if you want to go much shorter, you have to go into the UV and X-rays, okay? And try to produce an isolated attosecond pulses, because isolated attosecond pulse is automatically, you know, in the X-ray regime. So this is, we are going to use this relativistic compression technique that we have introduced with Natalia Nomova and John Nees, and which works this way. So here on the left inside, you have the single cycle pulse that we have just produced. And this pulse, of course, of very high intensity, because now we have a single cycle with energies in several joules level. We go and we are going now to focus the beam onto a specimen which of course is composed of ions and electrons, and because of ponderomotive force, which is very large, ponderomotive force is going, so this ponderomotive force is going to press on the electrons and leaving, you can see that here on this slide, we push the electrons, light electrons, and we leave the more massive ions, heavy ions in the back. And we are, of course, with this displacement, charge displacement, we are ready to build a very large DC field. And this very large DC field will attract back the negative ions, because the DC field is positive. They attract back the the electrons, and these electrons are going to fly back at the speed of light, or close to the speed of light. So we are in a situation where now we are coming with the lasers, which of course are going at the speed of light. which hit this mirror, which is also moving very close to the speed of light with Lorentz factor in a range of 1,000. And this light will be reflected by these mirrors, and the mirror will be, it will be compressed, okay, because also the reflected light is going at the speed of light. So we have something which is now a pulse compressed to really maybe the attosecond level and maybe shorter. Natalia did some simulations, and she shows that, of course, if we come as a function of the field, you know, which is in the axis, the field, we see the the pulses. Typically, the pulses that we can compress is something like 600 attosecond divided by A0, okay, normalized vector potential, okay, and so we quickly see that, for instance, you know, at 1, the intensity corresponds to 10 to the 18 or so watt per square centimeters. We can really now produce 10 to the 22, which means we are close to A0 of 100, which means that we can produce, we should be able to produce pulses in a regime of few attoseconds, okay, by using this technique. Now, if we really want to go much higher, we have to crank up the intensity, and we, in principle, if we could go to intensity with A0 of 10 to the 3, 1,000. And so the pulses that we'll be able to get could be, in principle, you know, close to the zeptoseconds. But of course, you know, if we are in a first, you know, round, if we go to 100 zeptosecond, also we'll be very pleased. But this is really, I think, really a way to produce, you know, the pulses as short as in the zeptosecond regime. Now, what is exciting is now, you know, if you have zeptosecond pulses, okay, and if you had just 1 zeptosecond pulses, you will produce zeta watt system, zeta watt. You know, very simply, of course, 1 joule in a zeptosecond is zeta watt, 10 to 21 watt, okay? Now, because it's a zeptosecond, 10 minus 21 second, okay, we are in a gamma regime, okay, with MEV light energy typically, okay. So what we could really do is we could now observe acceleration in solid. Why? It's because, of course, now this gamma is going to propagate in solid, and the solid is going to look like a gas, you know, when we're using the short pulses in gas. And we should be able to go into the TeV per centimeters, because if you look at the expression of the energy obtained by Wakefield accelerations, is really a strong function, of course, of the intensity, the density, the electron density. So we should be able to go into the TeV per centimeter, which, of course, is absolutely humongous. So, and of course now, if you have a zeta watt in lambda square, but where lambda square now is in the gamma ray or lambda X-rays, lambda. Nevertheless, very short, very short. That means that we could easily go into the 10 to the 29 watt per square centimeter, where we want ray to be, the Schwinger intensity. A light should turn into matter. Okay, this is, of course, very exciting. Now, one thing I want maybe a little bit fast. Just want to remind you the concept of Wakefield Accelerations. You know, of course, which has been demonstrated by, which has been proposed by Tajima and Dawson in 1979, and where really you're producing this plasma wave, and where the electrons are moving like a surfer on the wave. And you know, if you are doing this experiment in the visible, where really the laser is, you know, invisible, so the wake field now is in a regime of it's a plasma wave. The plasma wave which is produced now is significant, and we could get in the visible something like GeV, giga electron volt per centimeter, which is of course very large. This is where the visible, and remind you that the GeV machines, you know, can be something as big as the Soleil, very large. Now, if I want it now to move from gas and the solid, as I said, it would be a great idea, because the solid, the output, you know, electron beams are in the GeV per centimeters. Now, if we move to the solids, now it will be in TeV per centimeters. And so I have this two graph now showing the energy gain. Okay, the energy gain is really proportional to A naught square, A naught T square, times the critical electron density, and over Ne, okay, the density of the electrons in the material. So if you are using, if we are using gas, of course, the critical density with visible light, you know, is about 10 to the 10 to the 23, okay, or 10 to 21, something like 20, and 10 to the 21, and I'm sorry, I'm repeating. Sorry, I went a little bit too fast. The critical density, yes, 10 to the 21. And if you want to look at this expression, if you want the critical intensity at 10 to the 21, if you want to have a large NC over NE, then NE has to be very small, which means that you have really to work with low density gases at 10 to the 18. Now, if I really move from gas, I should say, if I move now from visible to X-rays, okay, I can use solid, as I said, okay, and we can go from now the critical density for solid in the X-ray is 10 to the 29, okay, for X-rays. And so this ratio of NC over NE is enormous. It's about 10 to the 6. Okay, so there's a huge benefit to go for X-ray regime. but of course they have to be intense. Okay, and so if we do that, this is of course is leading to absolutely very impressive result. And if you consider these TEV electron machines, which is at CERN, the LHC, the Large Hadron Colliders, this 27 kilometers is because we are using, of course, microwave technology. Okay, and that's the reason what we can get. We are using 27 because the gradients, acceleration gradients, is only in 100 or so MeV per centimeters. Now, going to the visible, as I showed, in the visible, then we can do it much better. Now this 27 kilometer could be reduced into something like 100 meters. And now if we're using X-ray, if we are using X-ray, of course, now we are talking about TeV per centimeter. So really you have LHC really could fit on the top of your finger, okay? And this, of course, is absolutely fantastic. It's very impressive because we could, if we get TeV over centimeters, which means that we could get PeV, okay, over few meters. And PeV, of course, we don't know how to produce PeV on Earth. We have just, they are only produced in the cosmos. So that will be really very important application because we could maybe study the physics of cosmic rays in this regime. Okay, now another applications of this very high intensity, very short pulse in a single cycle, right? I said single cycle, right? It will be ready to produce protons. And the protons are will be produced very, very simply by using a film of materials. And so we could excite this film of material with this single cycle, pulse in this regime. In this case, it will be invisible. Then the light ponderomotive force push the electrons, leaving behind the protons, and so the electron will fly, attracting in the back the electrons, which is negative charge, will fly in front and leaving the proton behind and attracting the protons. Okay? So we could, in fact, very simply by using single cycle, okay, we could produce really MeV protons, okay, just by using single cycle, as I said, will be much more effective, okay. But now, well, we have to use really a lot of energy to go into this regime. So, of course, now we can talk about applications. If we have protons, very compact proton source, we could, at a GeV level or fractional GeV level, then we could really now talk about proton therapy. Proton therapy, we know, is really the first choice of therapy because if you are using electron or X-ray therapy, and if your tumor is in the volumes of the tissues, then you are going ready to with electrons and X-rays, you are going to burn the healthy tissues. On the other hand, if you are using protons, you can adjust the proton energy and just burn the tumors, not burning the tissue which sits before the tumor. So this is a very important application. Anyway, so I'm going to stop here because there's many other applications, of course, of extreme light in the X-ray gamma ray regime, which I think is really the future now. That's the reason that we are working very hard with a number of groups trying to reach to this point. And and so with this kind of pulse, we will be able to really produce extremely large field, large accelerations, of course, large temperature, largest pressure. So if I think about the motto from Alfred Nobel motto, which is, invention for the greatest benefit to humankind, that I think this work, will absolutely fit this motto. Okay, so I'm going to stop here. I'm going to thank you very well, very much, and I will see you once the COVID is over. Bye-bye.
So thank you very much, Gerard. And I think you're there in person to answer questions. And we have two people monitoring the chat with questions to ask you. So I'll pass you on. I see Sean Cederberg is got his camera on, so I'll get him to ask you the first question.
Okay, thank you. And I'll remind everyone, if you have questions, please type them into the Q&A box at the bottom of your screen. I don't see any yet.
I can ask a question to start if you like, Sean.
Okay.
Thank you very much, Professor Mourou, for your very interesting talk. You mentioned that using the top hat, sort of a uniform intensity pulse allowed you to compress the light more tightly or to a shorter pulse early in the talk. I'm curious to know if not just the transverse intensity, but the transverse phase of the pulse is something you can manipulate as well, and what that would do to your ability to compress pulses. So for example, how would a beam with a uniform phase front compress differently from a beam that carried orbital angular momentum, for example?
Can you hear me?
Yes.
Yes, you can hear. I guess I don't quite understand what you want to do, okay? By using, could you repeat what you said?
Well, we're interested, you showed a top hat intensity function.
I see the top hat, of course, and I'm producing now with this top hat, uniform cell phase modulations,
right?
Across the beam, and now I can try to compress this pulse using chirp mirror, for instance.
Right.
Okay? So I don't understand exactly what you are proposing.
Well, my thinking has been, I know that within certain focusing regimes, that beams with different transverse phase profiles will compress differently. And so I'm wondering, within this domain of compressing to short pulses, if transverse phase profiles have an influence, and if so, if you could explain what that influence might be.
Yeah, absolutely. But that's the reason we really are working very hard to get the most uniform film, uniform intensity on the beam. Okay. Otherwise, I think it would be disastrous. For you couldn't really compress the pulse very nicely. You have to have a very uniform top hat.
Okay. Uniform in terms of intensity profile and also phase.
Yeah, intensity, yes.
Okay.
Yeah, this is really the goal. I mean, and I think we're pretty close now.
But yeah.
It is possible that the question and answer is not working correctly because I tried to get a question in and I can't do it. Sean, do you have questions?
I don't have any here. No, I think there must be a problem.
I think there might be a problem. So let me suggest something different. I know there are 114 people, which is an awful lot. So this may not work at all. But can we ask questions verbally, maybe one at a time? Could we ask questions verbally? Because it seems like the question and answering is not working.
Okay, actually, there is someone just got a question through, so it seems to be working.
Okay.
Yeah.
Maybe I don't know how to do it then. Maybe it's just me.
Okay. So we have still quite a bit of time for questions, so please, anyone who has one, feel free. Maybe I can ask one while we're waiting as well. I was curious about the femtosecond pulses and what would be required in terms of dispersion management and in really focusing them down into this lambda squared area and maintaining the space-time structure of the pulse. Does the technology exist, or and if not, I guess how would we overcome these challenges?
Yeah. No, I mean, you are right. I mean, we will have really right now, I mean, focusing this gamma beam will be a really major problems, okay? So right now we are really trying, but I think compressing the pulse in a time domain, I think maybe that will be more possible. Okay? And I'm sorry, the pulse will be compressed after that in a time domain or in space domain, you know, later on. But right now, we likely to compress it in a time domain and maybe mostly in a time domain, okay? And in a space domain, we will try to do as much as we can. But I know it's very difficult, of course, to have both.
Okay, thank you.
Gerard, I guess since there's a silence again, can I ask you about background? So you've used the thin film compression technique, and you want to use it with more or less a top hat surface. So it seems to me that has some similarities to fibers, and there was always a problem with the background from the original pulse duration that didn't get well compressed. It seems to me this is also likely to be a problem here. So what do you do about keeping the background radiation from the initial 25 femtosecond pulse under control, or because you need
of course, and you are absolutely right. So I think what we will do is trying to clean up the pulse, you know, with technique like plasma mirrors and things.
Okay, do it after.
We're really, but I think we are not going to get a compressed. I'm not, you know, I think I have to be realistic, and we are not going to compress the pulse by a factor 100, just like this. Okay, it's going to be very difficult to do a very, very perfect job, and I think we will have to resort to technique that we know using plasma.
Okay. Yeah. That was the question. I tried to type in the question and answer, but I still have not managed to get it in there. So that was my question.
Okay, very good.
We're starting to have some questions come in now.
Okay.
So I'm happy to ask some of them. Professor Mourou, can you comment if the subatomic particle community is already setting up a project based on the TeV per centimeter acceleration opportunity? In other words, are they considering the future top-of-the-line accelerator to be optically driven, or are they still trying to see if that technology can be realized before they begin planning in that direction?
No. I think it's it's kind of very new, of course, technology, and which really need a lot of work, okay, to be demonstrated. So right now, of course, they are very well aware of laser accelerations, in a visible, okay. Then we were really GeV per centimeters now has been demonstrated, okay. And of course, when you are a scientist, you are trying to move to at least trying to conceive, systems which are really beyond what you can do immediately. But right now, I want to say, right now, it is possible really to produce with the lasers, with conventional CPA system, pulses in a gigavolt, giga electron volt per centimeter regimes. This is what we can do now. And I think maybe by moving to the UV and to the X-rays, we'll be able to go to much higher. But this is just, I wanted to give you an idea, okay, to make you dream about possibilities that could, in the next 10 or 20 years, be demonstrated. Thank you.
I see. Thank you. I have another question here from Professor Loix. The Schwinger field is calculated for a quasi-stationary electric field like that of visible light. As you go into the gamma ray range with the laser photon energy, will the vacuum break down and change?
Well, I mean, of course, the Schwinger field is calculated as the work that the field that you are doing, the field is doing over a Compton wavelength, right? It has to be greater than 2 times m naught c square, okay? So if you take the wavelength of Compton wavelength with the field, which is a Schwinger field, you have to go over 2 times m naught c square to produce an electron and a positrons, okay? So, but gamma rays, have period frequency which correspond to this. So, I mean, we may not we are almost in a, with gamma ray, we are in a kind of slow envelope, conditions. So yeah, maybe it's challenging, but I think it's not. I think we discussed it, and I think if you are in the X-ray regime or gamma ray regime, X-ray gamma ray regime, you are still in a regime where you can really use, the field as almost a quasi-DC. Is it okay?
Yes, I think so. Thank you.
I suspect, since everybody is quiet, that we've reached the end of the questions.
Yes.
And I'm not sure if everybody has got a chance to ask them, so that's something we have to sort out. You're our guinea pig, Gerard. This is the first time we've tried organizing a meeting of this scale this way.
And that's the first time also, you know, I'm submitted to this exercise.
Maybe you could turn on your camera and everybody could see you as I say thank you.
So I thank you very much.
Well, I wanted to say that I've known Gerard for many years.
I really thank you very much.
And over many years, I've known him, and he's always been forward thinking, pushing the envelope on what lasers could do. At least to me, I see that when you went to Europe, the extreme light infrastructure came, and I associated almost completely with you. Your ability to see the future and sell it to everyone is absolutely amazing. Actually, can I ask you, just as a way of concluding, are you surprised at the impact of Chirped Pulse Amplification? Probably many people have asked you that, but they're in all laboratories around the world, my laboratory and many others. Are you surprised at its take-up, how much impact it has had?
Paul, I'm sorry, the sound was not really very good, so I missed really a big chunk of your question.
So I asked in a way of ending, I said, I don't know if you can hear me again. Let's give it a try.
Yeah, that's nice.
Are you surprised at the impact of CPA? Looking back on it from the night, now looking back to 1980s and what you thought then, how does it look from your point of view? Is it bigger impact, less impact? I can't imagine it's less.
No. It was, I was not expecting, really, my gut feeling was really that it will have a big impact, but not that big.
Yes.
You know, but I thought that it was going to be a major impact. You know, a lot of things, you know, between the first experiment that we did with Donna by using optical fiber for stretching, neodymium glass and grading, you know, for compressions, you know, neodymium glass, you know, not as no, it's very small bandwidth, you know, compared to now Thai sapphire and now this technique also to stretch the pulse with the laser. So many novel idea came and make the CPA now a big success, but it was not just on the basic CPA. You know, we had to work very hard. I mean, we had to work, what, 20 years, in fact, to develop CPA the way we like it now.
Well, let me again just end by thanking you very much for participating, for giving a very interesting talk, and we're happy to host you back for at least a third or fourth time in Ottawa. So thank you.
Very good. Thank you all, and I wish you a very good continuation for this Schawlow-Townes meeting.
Thank you.
Bye-bye.